Okay. Hello, welcome everyone to strong field laser physics. Today we will move, we will close the discussion of the tunnel ionization rate and return to photoelectron momentum distribution. And to conclude the discussion, we will now actually first move from the one-dimensional treatment of tunnel ionization, or I should say one-dimensional treatment, to the three-dimensional treatment, yes? And we will see that there's slight differences, but the general behavior remains essentially the same. Okay, can you, yes, the PowerPoint. So we have here, so these, oops, in the, okay. Yeah, so in the previous two lectures we discussed we discussed the WKB method to for tunneling, and now I will make a few remarks on the generalization to three dimensions. We will not do this calculation analytically because it's quite lengthy. And in the seminar, I will lose a few more words about the ADK formula. And then today's lecture, the first part will focus on the perpendicular momentum distribution. Excuse me. Yeah, which obviously arises when you move from one dimension to three dimensions, yes? Then you have not only the momentum along the polarization, which I would call longitudinal momentum, but also the transversal momentum, or perpendicular to the polarization. And then in the second part, we will really return to the photoelectron momentum distributions and first introduce the canonical momentum, and then apply this to a very interesting experiment known as the attoclock experiment. Okay, so regarding the previous result, this is the result that we obtained for what actually? Yeah, so it's 1D, it's ionization in 1D, and so our electron is bound. And what is it bound to? Yeah, it's bound in a potential. What kind of potential is it? Yes, in reality it's a Coulomb potential, but that's not what we calculated. What did we calculate? Yes, a delta potential, exactly. Yeah, so it's a 1D delta potential. And we saw that the result differs quite a bit when you use a Coulomb potential instead. And what's the important word there? Or the important effect that occurs in a Coulomb potential but not in a delta potential? Yes, barrier suppression, or over the barrier ionization, exactly. Yeah. So I gave away the answer to this, so no one, I guess no one thinks that anymore. Yeah. And so the result in three dimensions actually looks like this. Yeah, so it's a lot more terrible, but it's not as terrible as you may think. So for example, when you do this for a hydrogen atom where the principal quantum number n equals 1, and then the angular momentum and magnetic quantum numbers equal 0, then all of these terms here, they actually just become ones and zeros and so on. And so this, all of this just turns into a 4. And then this is the result here for the ionization rate from a hydrogen atom, but not a real hydrogen atom, but one that is modeled with a delta potential. Yes, and now how do you obtain this momentum distribution? This would be done by using parabolic coordinates. Yes, so you're obviously all familiar with spherical coordinates, where you have two angular coordinates and one radial coordinate, and here it's a bit more complicated. Yes, so the transformation from the Cartesian coordinates to these parabolic coordinates is given here, and this is an illustration of the the planes where one of these numbers is constant. Okay. Yeah, so these are the parabolic coordinates for tunnel ionization in 3D. And then we had, then in the script you will find a short chapter about the ADK formula. So the ADK formula is really nothing else but averaging the instantaneous ionization rate that we derived earlier over a laser cycle. Yes, we will look at this in the seminar and now move on to the perpendicular momentum distributions. Yeah. Unless there are now urgent questions on the ionization rates. Yes?
I don't think it's urgent, but is it like I don't get the connection between the tunneling probability and the tunneling rate.
Yeah, good question. So the question is about the connection between tunneling rate and tunneling probability. Yeah, so the tunneling rate is has the unit 1 over time. Yeah, so it's the number of electrons that tunnel within a given amount of time. Yeah, and the ionization probability is just a number. So you can ask, is the atom ionized by this laser pulse? And there's a certain probability to it. The connection between the two is that when you integrate the ionization yield over time, that you obtain the ionization probability.
No, I think I meant like the probability of tunneling.
Yeah.
Because we took the amplitudes of the wave functions, and I think this is a probability, right? Not a rate.
Okay, I know. So let me see. Yeah, so these are we use the amplitudes, right? We use these amplitude factors. What's the? Okay, can you repeat this?
By the Bohr frequency or something, or multiply the Bohr frequency to get to a rate, and that's not changing the result because it's 1 in the atomic units.
I see where the problem is. I think maybe you're not here in the seminar, are you? Yeah. Okay. Yeah, maybe afterwards. Yeah. Okay, but anyhow, this what we get there is the tunneling rate. Yes. Okay. Then now let's move on. So, what is shown here is the 3-dimensional momentum distribution of photoelectrons emitted from, I think in this case it's an oxygen molecule. Yes. So now we're moving from 1D to 3D. Yeah, and then it makes, of course, sense not only to look at the energy, but rather at the velocity distribution or momentum distribution, which is really the same number in atomic units when you look at electrons. Yes, because the mass of the electron is 1 atomic unit. Yeah, so what here is the laser polarization, and you see that the main component, yeah, so the is along the laser polarization. Yeah, so the momenta or velocities are larger along the laser polarization. Here it extends up to approximately 3 atomic units, whereas in the plane perpendicular to the laser polarization, that would be here, you have only 1.5 atomic units or so. And before we actually go back to discussing this distribution here along the polarization, we are now asking how this width comes about. Is it clear to everyone what's shown here in these plots? Yeah, so this is a logarithmic scale. The color indicates the number of electrons per little momentum bin. And actually, this would be a 3-dimensional function. Yeah, number of electrons per momentum bin in 3 dimensions. And because that's hard to look at, they are displaying here the projections onto all 3 planes. Yes, the ZX plane, the ZY plane, and the XY plane. And now we're actually concentrating on this plane here. Okay, so at the momentum, we already discussed that the momentum along the laser polarization is given through the acceleration in the laser field. Does anyone have an idea where this momentum distribution could come from? What it could originate from? Yes, please.
Like the weak field, like the motion.
The magnetic field. That's an interesting idea. That's not the case, unfortunately. Yeah. So if you think of a hydrogen atom, yeah, the electron is of course localized in this atom, yeah, to roughly 1 atomic unit in space. And now we can think of the Heisenberg uncertainty principle, and then it's clear that there must be some momentum width connected with this localization. Yeah. Now in this chapter we will actually look into the details. And can we have the iPad, please? Okay. The other pen. Okay, we have now, this is section 3.10. Perpendicular momentum. Oops, that's interesting. Maybe I try to disconnect it and reconnect it. Or I just write on the other iPad. Yeah, I don't think it's very nice to see this all the time. Can you turn it off, or should I disconnect? Okay. Hang on. Okay, what happens when I change the cables? Then this one should appear there. No. Here. Now it's okay, isn't it? Okay. But they're not. Seems they're not talking to each other right now. Okay, so 3.10, perpendicular momentum and orbital effect. Okay, so the motivating question is, where does the momentum perpendicular to E originate from? And then our idea was on the uncertainty principle. Delta x times delta p is larger than h bar over 2. And then h atom in 1s state and the radius of the Bohr orbit is 1 atomic unit, and that means delta P must be 1/2 over delta x using atomic units. And actually, we actually know the spatial orbital. Yeah, and then that means we can also calculate the momentum function, the momentum orbital. Yeah, so we have here the momentum space orbital, and the momentum space orbital. Yeah, so that would be phi, phi instead of psi of p. This is connected through a Fourier transform to the spatial wave function. And we can perform this. Yeah, so we can look up the ground state of hydrogen, then perform the Fourier transform, and what we find is actually this result here: square root 8 over pi times 1 over p squared plus 1 squared. Yeah, so this is the momentum space orbital. So you can see here that the maximum is around 0. Yeah, so it's but it doesn't deviate at 0 as the spatial orbital does. Yes, the spatial orbital has this e to the minus r dependence, and this one does not. Okay, and now if the momentum momentum space orbital is actually related to what we measure, this would have the interesting implication that we could actually image the orbital wave function using tunnel ionization. And because we use short laser pulses, we could potentially even image changes in the momentum space wave function on a femtosecond time scale. So maybe I just write down this question: can we image momentum space? I shouldn't actually say a wave function, because we can never observe the wave function. We can only observe the wave function squared, and that would be the density of the electrons. So can we image momentum space electron densities? Using tunnel ionization.
So what is the wave function in the p space, in the momentum space?
Yeah, this is the wave function in the momentum space. What?
Okay.
Yes? Yeah, so this describes, just like the wave function describes the localization probability, yeah, the probability to find a particle in a certain space. Here it's the probability, or the wave function squared is related to the probability for a particle to have a certain momentum. And this is, of course, connected through the Fourier transform to the spatial electron density. So the question, and whether we can do this or not depends on what happens to this wave function when the electron tunnels into the continuum. Yes, so what happens to psi, let's call this orbital of P, when the electron tunnels? By the way, why can we not observe the real space density directly? Yeah, because space is not a conserved quantity, but momentum is. Okay. Can we briefly switch to or show the PowerPoint in addition? Doesn't get transmitted. Ah. What about now? There it is. Yeah. Okay, for this, can you show it in addition to the iPad, please? Yeah, wonderful. So we have here a visualization of the potential that we previously drew in 1D in 2 dimensions. Yeah, so maybe I draw here what our potential. So our potential is, of course, the part of the laser minus the part from the atom. And previously in 1 dimension, now we have here this laser component. Previously in 1 dimension, we had it looking like this. And now we assume that our laser field is polarized along Z. Yeah, so it distorts this potential in the Z direction, but the direction perpendicular to the laser field is actually remained unchanged. You could change this by using circular polarization. Then this plane here, this would actually rotate. Okay, and now we're adding, so previously we were looking at this direct route of tunneling, yes, so along the laser polarization, because we only had 1 dimension, and now we consider here a perpendicular momentum in addition. Now, qualitatively, what would you expect for the tunnel ionization rate or probability when you add a perpendicular momentum? So would it remain unchanged? Would it increase, decrease?
Basically unchanged because it's not going in the direction.
So you think it would remain unchanged?
Maybe increase because the distance we have to travel wouldn't be very nice.
Yeah, the distance, yes, the distance is a bit longer. Also, well, the height should be the same, but the distance is a bit longer. Yes, and then it remains changed. And then, of course, the wave function decays exponentially under the barrier. So it is quite drastically reduced. Yeah, so when adding P perpendicular, we expect the tunnel ionization probability to decrease, probably exponentially. I put these in parentheses because this is a guess at this stage. And by the way, P perpendicular is simply px plus py squared square root. Yes, and for E equals Ez. Maybe a better way to write this is 0, 0 Ez. And because of this expected strong decrease, we can expect that the perpendicular momentum will remain rather small. Okay, now let's let's remind ourselves of our previous result. Yeah, so for 1D tunneling, we found that the transmission probability is given by these by the ratio of the amplitudes squared after the tunnel and before the tunnel. And we wrote this as minus 2 alpha, where alpha was given by an integral essentially over the momentum along the z direction under the tunnel. And now we will use the same approach for 3D. In 3D, we have P equals Px, Py, Pz. And we can also write this as a perpendicular momentum and a longitudinal momentum. Yeah? And therefore, we can also rewrite the equation for this decay parameter alpha as the same type of integral. Yeah, from the start of the tunnel to the exit over the momentum, which actually can depend on z. And now this can be written as P, maybe it's makes more sense to write z first. Okay. Now we need an expression for, we somehow need to solve this integral, and we will it will make our lives easier if we can actually split it up in one component that depends only on Pz, because we have solved that one before, and one component that depends only on the perpendicular momentum. And that is then what we want to solve. Yeah, and we previously made the remark that our momentum should remain rather small. Yeah, and then, of course, what we do is the Taylor expansion. So we assume P perpendicular squared is much smaller than Pz squared, and write a Taylor series. Okay, so we have here Pz squared plus P perpendicular squared, and now so we will expand this around P perpendicular equals 0. Yeah, so the 0th order term therefore is simply Pz. And now we need the first order term, dP over dP perpendicular at P perpendicular equals 0 plus times P perpendicular, of course. That's the first order term, and now we also need a second order term. So it's the second derivative of this momentum, of the total momentum with respect to the perpendicular momentum, and yeah, higher orders which we will not need. Okay, so first let's calculate the first derivative, dp over dp perpendicular. Yeah, so we have the square root here. So this becomes, this is to the power of a half, so it becomes minus a half. So this goes in the denominator. And we get 1 over 2 from the exponent, and now we need the inner derivative, which is 2p perpendicular. And now if we plug in p perpendicular equals 0, then we will actually find that the first order term is 0. Yeah, which is actually also what we expect, because the potential looks the same on this side and on that side, and therefore the first order term must be 0. Okay, so we take the second derivative, d2 dp here. And that now we first take the derivative of the numerator, which is 1, over pz squared plus p perpendicular squared square root plus, and now this part, that's minus 1 over 2 from the exponent, p perpendicular, and actually to p perpendicular times 2, because that's this inner derivative here, divided by pz squared plus p perpendicular squared to the power of 3 over 2. And again, we evaluate this at p perpendicular equals 0. And when we do this, this term is again 0, and that term here is very simple. It's simply 1 over pz. Okay, so we find that we can write square root pz squared plus p perpendicular squared as pz plus 1 over 2 p perpendicular squared divided by pz. Yeah, this 1/2 is that 1/2 here. Okay. So for the for this attenuation parameter alpha, we can now write the following expression for alpha. We have alpha equals this first integral here, the one that we solved before, and now the one that we have to solve, 1 over 2, modulus of p perpendicular squared over pz dz. Yeah, and this is alpha 1d, the analytical solution that we had before, and this is the correction term. Correction for the perpendicular momentum. And now, of course, we do the same that we did before, namely we move away from this Coulomb potential that we drew here and use a delta potential instead. Yeah, so for the moment, we won't need this one anymore. Good. Wait, does this work again? No. Okay. Yeah, so again, we consider a Coulomb potential. Sorry, not a Coulomb potential, a delta potential. And so our potential now actually looks like this. In Cartesian coordinates, we have a delta, x, y, z. Yeah, so this in the three-dimensional plane, this is basically infinity at 0, 0, 0, and 0 everywhere else, with the property that when you integrate over it, the result is finite. Okay. And for the important here is that when we take the derivative of the potential with respect to x or y, we obtain 0, which means there is no force acting in the x or y direction. Yeah, so dv over dx equals 0, and this is also dv over dy. So there's no force in x or y direction, and this means we can assume that our perpendicular momentum remains unchanged in the tunnel. Has no force in x, y, and therefore p x, or let's just write p perpendicular. However, the amplitude will be attenuated, yes? But this with this assumption, of course, it's much easier to solve the integral that we need to solve. Yeah, and we still have pz equals minus e plus v eip minus this still holds for the momentum under the barrier in that direction. Okay, so now let's solve the correction term. Yeah, so this we still needed the expression for the tunnel exit. That's the same as before. Yeah, so we just have to set E times Z equal to the ionization potential. Yeah, and so the tunnel exit will be the ionization potential over the electric field strength. Okay, and now we solve the integral. Yeah, this. Pardon?
Pz is imaginary?
Yes, Pz is imaginary here, but as before, we'll just treat it. We'll just pretend it's not by using the absolute value. Yes, and okay. And now we solve from 0 to EIP over E. P perpendicular squared. Now we plug in this expression here for pz, 2 EIP minus ZE dz. Since the perpendicular momentum is constant, we drag it in front of the integral, and then we solve the integral and obtain minus, yes, there's a minus here, 2 EIP minus ZE in the limits from 0 to EIP over E. Plug in the limits. Zero minus square root EIP. And then we have this here, square root, oh, there's a 2 missing. Yeah, the 2 is already missing above. 2 EIP, yes. 2 EIP. And this term we encountered before. And even if the units don't look like it, this is a time. And this is our tunnel time that we found when we derived the Keldysh parameter. I call this the Keldysh tunnel time. So if you want to look it up, it's 3.21. Yeah, it's related to the Keldysh parameter, by the way, by gamma equals this tunnel time times frequency. Yeah. Okay. So this is now the attenuation this is the correction to the attenuation parameter. Yes. So we still want to write the transmission of the barrier, yeah, to get the full picture. Yes, please.
Regarding the Z out, is it the location where the electric field is equal to the binding energy?
Yes, exactly. Yeah, I drew this here, right? So if we assume here, yeah, this would be Z out. Yeah, only here I drew a Coulomb potential, or at least something close to it, whereas the calculation we did for a delta potential, which means that the numbers are slightly different. Okay. Now, yeah, as I said, this is the correction to the attenuation parameter. So let's write the full transmission of the tunnel barrier. So the transmission of the barrier is T, P perpendicular equals exponential minus 2 alpha 1d. That's the term we had before. And now we have, in addition, this term here, yeah, with P perpendicular over 2, but we have another 2 here in front of it, so we can skip it here. P perpendicular squared times tau tunnel. Yeah, and this you could also write as, yeah, because these are exponential functions. So you could also write as as such an expression where this function here could be called the tunnel filter. Yes, essentially a low-pass filter for momenta. Yes, the electrons with that means electrons with a low momentum have a higher probability to be transmitted through the tunnel. And now, if you perform a measurement, because you usually don't know how many atoms there are in your sample, which you illuminate with your laser. Therefore, you actually never know the absolute probability for tunneling in your laser pulse. You can only estimate the number of atoms in your ensemble that's basically the number of atoms in your laser focus. You usually don't know this. But when you measure the momentum distribution, what you actually observe is this filter function here. Yeah, and let's take a look at that. Yeah, so for example, when you for a helium atom, helium has the advantage that it also has a 1s orbital, of course. Yeah, and so the spatial wave function and the momentum wave function is essentially the same or very close to that of hydrogen. Not exactly the same, it's close to that. So 1s orbital, and the ionization potential of helium is very large. It's 0.9 atomic units. Yeah, so that's 24.6 electron volts. And we use here an intensity of 1.3 times 10 to the 15 watts per square centimeter. Why can we not use this intensity for atomic hydrogen? Yeah. Yes, it's over the barrier. Yeah, this intensity is way over the barrier for atomic hydrogen. Yeah, and then there's no tunnel to go through. So what we discussed made no sense for makes no sense for hydrogen. And the other reason I am using this value is because because there's a measurement for this that I did a few years ago, and I didn't have an atomic hydrogen source to do it. Okay. Yeah. So we have the momentum wave function. So we have psi 1s of p equals 1 over p plus 1. And now this actually goes to I have to rewrite this. So we have the momentum wave function. We use the result from earlier on, or the expression that I gave earlier on, and this is here. Is this? Yeah. So this is the momentum wave function, and now what we measure is the probability distribution. So we actually have to square this. Yes, and then into our expression actually goes the tunnel. Wait, hang on a second. Into our expression goes the momentum squared. I'm just thinking that I used a square too many here. Yeah. So okay, I actually skipped the prefactor because it only scales the result. Yeah. So this is the momentum wave function, and this actually has a square here already. So I didn't use a square too many. Yes. And so we need to square this, and then we actually get the fourth power here. Good. And then our tunnel filter is exponential minus p squared over 2 tau t. And what we measure is, so it's the yield and as a function of the perpendicular momentum. This is proportional to the wave function squared, 1s of p times the tunnel filter. And when you plot this, you actually get two decreasing functions. And so which one is which? So this is actually a logarithmic. We have here the momentum, and here we have the logarithm of the electron yield. And we observe that this decreases here like that, and this would be the tunnel filter. And then we have a slightly steeper decreasing function, which is related to this orbital. But what's actually measured is the product of the two. Yeah, and this goes like that. And that actually agrees quite well with the experimental data. So they sit somewhere here. Okay. Good. I'd like to, before we conclude this session, this first session, I'd like to, here. Yeah, so this is, can you switch back to the presentation? Yeah, so it actually looks like this. So there's a deviation at lower momenta. There's a question?
Why did we divide by 2 in this tunnel filter?
We actually, here.
Yeah.
Yes, that's a mistake. Thank you.
And we are just taking the perpendicular, like in the wave function, we're just taking the perpendicular part because that's the only one we're looking at.
Yes, exactly.
Okay.
Yeah, so this is integrated over all longitudinal momenta. Okay, now if you go back to the PowerPoint, yeah, so I forgot that I brought this slide, to be honest. Yeah, so there's a deviation at larger momenta, which is actually larger. Then the deviation is stronger than I expected. Yeah, but this actually makes sense. Yeah, because we put an assumption into our derivation, namely that the perpendicular momentum is small. That is actually not so small here. So above 1 atomic units, it's not so small. And so from these experimental results, it looks like the transmission is actually higher than expected at large momenta. And so as a final thing, I wanted to advertise a little bit these results that we obtained a few years ago, where we prepared an argon atom in these two different electronic states. Yeah, so these the red and the blue wave functions here, they indicate or they illustrate the electron distribution in these two states that we prepared, and then we ionized an electron, ionized the atom again and removed an electron from these states. And well, these are the results that we obtained. And the difference is really not very striking, is it? And the reason for that is that what we measure there is actually the tunnel filter function. So what you should be mostly looking at is this one here. Yeah, the lower energy, this part here at negative momenta, this is actually cut away because this is not the signal that interests us. So we used this certain trick that allowed us to separate the signal of interest from that that's not interested and not particularly interesting. Yeah, but here you really have the signal from this wave function and that wave function. it really looks the same. So we need to remove the tunnel filter. And the simplest trick to do this is to calculate the visibility. Yeah? So you take one distribution, subtract the other one, and divide by the sum. And then what you get is this one here. Yeah? And you can interpret this here as a top view of this red peanut-shaped distribution with this blue donut-shaped distribution around it. Yeah, and of course, we don't measure colors or so. The electron distributions don't have colors, but this is the difference of the signal. Yeah, so red means there is more signal in this distribution, and blue means there's more signal in that distribution. If you take the if you do this differential measurement or the differential analysis of your measurement, then you can actually retrieve the impact of these different orbital wave functions. Yeah, and that can be compared to theory. Yeah, the theory, of course, looks nicer. Yeah, but that's just how it is. Okay. Yeah, we conclude the first session and do a 5-minute break. You can take the time to think of some questions that you may have or chat with your neighbor for a couple of minutes. And then we'll be back in 5 minutes.